Arcane, the unprecedented cinematic masterpiece bestowed on us by Riot Games that scaled Netflix charts immediately after its release. Everything from the plot to the characters to the animation is stunning. And what's the source material for this absolute fucking Gesamtkunstwerk? League of Legends, of all things. Nobody expected Arcane to be this good. Even League fans expected mediocrity at best. And now what do we do with all this new lore? What do we do with all this new information, these new questions? Hi, I'm Natalie Grace Frankovich, and today I'll be unraveling the most relevant, most anticipated, most burning question that Arcane has left us with. And you may think that we'll be theorizing who in the council is gonna die, or what happens with Jinx and Vi's relationship, or if Echo and Victor end up becoming their fully fledged in-game characters, or if Vander gets experimented on by Singed to become Warwick. But no, we are academics and scholars. We do not fret of the characters and plots of these fictional accounts. Nay, we delve into the scientific implications and laws of these fictional realms. You know, real science. But will we be delving into just any old science, like the mechanics of Jinx's monkey bomb, or chemistry in Shimmer, or the ethically abysmal experiments that Singe gets up to? No. Get out of here. Who gives a hoot? What we care about is that juicy little catalyst that drives the conflict throughout the entire season. Every side plot, every character is connected by one thing, and that is the power of Hexgems. So in order to approximate the theoretical power yield of a Hexgem explosion, we need to derive a formula that uses only the information given to us in Arcane, as well as known physical constants, which we're just going to assume to be the same as in our world. To do this, we're going to use dimensional analysis, which uses formula manipulation and proportionality of units to simplify an equation into a workable expression that fits our specifications and limits. In other words, we're going to take laws and formulas that have variables that we don't know, and we're going to put it in terms of variables that we do know. Smash cut. Hopefully, if I do my editing correctly. Dimensional analysis. In order to find power, we're going to denote power as capital E for energy in terms of kinetic energy, which is 1 over 2 mv squared. M is mass, v is velocity. Here we're just going to rewrite it in terms of units of mass, length, and time. It's mass times length squared over t, because we have mass, obviously, and velocity is in meters per second, so it gets length instead of meters and time instead of seconds, and squared because of the squared. So now we have to find what quantities we're going to apply to these units. We need length, time, and mass. So for length, we're using r, and it's going to be raised to the power of n that we're going to solve later on, just because we know that it's raised to some power here in this final result that we're looking for. And t is going to be in time. Since it's not raised to any power, it's just going to be t. And to add the mass without actually needing to use mass or anything, we're just going to use density of air, which is in mass per meters cubed, which is going to give us mass over length cubed. Starting with proportionality, we're just going to take each of these three quantities that we discussed here and put them proportional to E to see how they're going to be used in our final equation. So this is exponentially proportional to E, which means that as R increases, so does energy. This one is inversely proportional, time, and so we're denoting it as 1 over t, because as time increases, energy is going to decrease and approach 0. And for density, they are directly proportional, so as density increases, there's no change in energy, because the air density is actually just going to be a constant in this case. Looking at these from a real world perspective, we can see if the radius gets bigger, if there is a larger scale of explosion in the same amount of time and the same air density, then that means there has to be more energy to create that larger explosion. If it takes more time to create that same radius of an explosion, then that means less energy was used. That was so good. So for the last part before the calculations, we just take energy proportional to all of our values here raised to arbitrary values. So radius to the A times the B and density to the C. And we're going to solve for A, B, and C and end up with our final equation over there. So first we're going to rewrite this as m to the power of 1, since m is just m on the numerator, l to the power of 2 because it's l squared on the numerator, and t to the power of negative 2 since it's t squared on the denominator. These are just going to help us find what our A, B, and C values are by giving us a desired end product. So taking our L and our density in terms of units, we have L to the power of A, because in this case it's just L to the power of 1, and we're going to distribute that A to the power of B for the same reason. And since density is mass divided by length cubed, we have m to the c times L to the negative 3c. And we can just simplify that to be m to the c times L to the A minus 3c and t to the b. And that gives us our c and b values really easily because they're just directly proportional this way. So c is equal to 1 and b is equal to negative 2. This way we can find our a value by substituting c for what we now know it is as 1 and setting it equal to 2. So we end up with a minus 3c, this expression here, equals 2, which gives us a equals 5. And then we can put all of this into our final equation here. Since a is equal to 5, we have r to the 5 times t to the negative 2 and density to just the 1 power, which is just density. So we end up with density times radius to the 5 divided by time squared as our final thing. Okay, so I got 2 good instances from the first act of Arcane that gives us a decent idea of the radius of the blast and the time of the blast. So the first one happens in the first episode of Act 1, and it is in Jace's apartment where Powder drops one of the Hexgems and it just bounces and then explodes. So we can approximate the dimensions of the room and how much of the apartment gets taken by the blast. So we can get a minimum radius of about 8.8646 meters. And I timed it to be about 2 seconds for the blast. So I put all those into the formula, and that gave us about 16,832 joules of energy from that. And then the second instance was from the third episode of Act 1, where Powder sets off the monkey bomb and kills her family. Spoilers. So the radius of that could be approximated to be about 9 meters based on the bridge that it scales. And the time for that was about 2.4 seconds. Given that information, we found 12,609 joules was the approximate energy yield of that. By averaging out these 2 approximations, we get 14,720 joules of energy as the approximate theoretical power yield of raw Hexgems. My work is done.